How's everyone doing today? We're going to get started with our 5.3 day 2, and this is all about concavity and second derivatives. So in my class, this is kind of meant to be a review. So hopefully you're coming into this with a little bit of knowledge about how second derivatives work. And if not, we'll try to clue you in as much as we can. So let's get started with this new one. Like all of the chapter, we're going to be framing this with this is zombie movies, and this zombie movie is White Zombie. This is actually the movie that the band got their name from. I don't know if you remember the band White Zombie or not, but this is that movie. So let's take a look at what we have here with concavity. And you will notice over here we have a piece of a graph that shows concave up and concave down portions. What you notice here is with the concave down portions, the red slopes here. As we move from left to right, those slopes are actually decreasing in value. So we're getting less negative, or less positive actually, and we're approaching zero slopes. And so when we say concave down, that means as we read the graph from left to right, the slope is actually decreasing. Looking over here at x equals 0, we've got a place where the slope is actually equal to 0. And to the right of that, if we have a section that's labeled concave up like we have here, what that means is that the slope is increasing. So we're getting more positive. So concave up means that the slope is getting less positive, and concave up means that the slope is getting more positive. Concave down, less positive. Concave up, more positive. And down over here we have a really popular saying that we have, and that is concave up is going to be shaped like a cup, concave down is shaped like a frown. Should you ever need a mnemonic device to remember which is which, up like a cup and down like a frown is not the worst one you could go with. Moving on with that, from all of those definitions, we've got the curve of did you notice that concave up is whether f prime is increasing or decreasing? So the curve is concave up if the derivative of f prime, which would be the change in the slope, is positive, meaning that the slope is increasing. And concave down would be if the derivative of the slope is negative. And so that's why we have f double prime greater than 0 means concave up. F double prime less than 0 means concave down. For this first problem, we're going to examine the concavity of the graph f of x equals x cubed minus 8x squared plus 5x plus 14 on the interval x is between 0 and 5. So when is this concave up and when is this concave down? First thing we want to figure out is what are the equations of f prime and f double prime. Well, f prime is just the derivative of f, so what do we have? So the derivative f prime of x is 3x squared minus 16x plus 5. That's handy for us to know, and we need that first derivative if you want to get to the second derivative. So what's the derivative of 3x squared minus 16x plus 5? Well, that's 6x minus 16. And we can do a little bit of analysis here, and we can look at it and say, well, then when is a second derivative equal to 0? And that would be what? 16 over 6, 8 over 3. And then our next task here is to go ahead and fill out this chart with values of the derivative and the second derivative. So I'll give you a couple of minutes to do that. If you want to pause it for more time, go ahead and pause it. But if we evaluate the derivative and the second derivative, we get these values. And if we take a look at the second derivative, we notice that here at x equals 0, the second derivative is negative 16, negative 13, negative 10, negative 7, negative 4, and negative 1. So that means that the slope is, or the f double prime is increasing, getting less negative. Actually, I'm crazy. We should be looking at f prime. So let's take a look at f prime. The slope, what's happening to the slope? Well, at 0 we have 5 to negative 2 to negative 8 to negative 12 to negative 15 to negative 16.25 to negative 16. Okay, so something happened here between x equals 2.5 and x equals 3. Notice that the slope is decreasing, and then at some point, somewhere around, actually we can probably say between 2.5 and 3, the slope is going to start increasing. So we're going from negative 16.25 to negative 16 to negative 14 to negative 11 to negative 6 to 0. So the slope is decreasing until some point, we don't actually know where, but it's probably somewhere between 2 and 3. The slope is decreasing. And then from some point between 2 and 3 all the way to 5, the slope starts increasing. So since the slope is decreasing from from 0, x equals 0 to x equals 2 point something, that's where the graph is concave down. Slope is decreasing, concave down. And then from somewhere between 2 and 3 to 5, that means our slope is, our slope is starting to increase. So that means we have concave up. So here we can see in the yellow section, we've got slope decreasing. In the blue section, we have slope increasing. And then there's this gray area, or green area, I guess, right around x equals 2.5, where the slope stops decreasing and starts increasing. Where is that point exactly? Well, I probably alluded to it earlier, but that point is going to happen when f double prime is equal to 0, which is 16 over 3, or 16 over 6, which is 8 over 3, which is 2.6. So at 2.6, the slope starts to increase. Now, let's see how that plays along with the second derivative. Now for the second derivative, notice that here we have places where the second derivative is negative. And that should correspond with concave down. Okay. And then here, from, well, now we know it's 2.66. From about 2.66 to 5, now we have places where the slope, where the second derivative is positive. Okay. So at 2.6, the second derivative changes from negative to positive. So that is our, what we're going to call our point of inflection. So at x equals 2.6666, well, 2 2/3 really, f double prime is going to change from negative to positive. And like we said earlier, that's going to be a special point. That place where the slope, where the function changes concavity, is called the point of inflection. So if f of x has a point of inflection at x equals c, well, f of x needs to be both continuous and differentiable. Looking for points of inflection has a lot of similarities to finding local minimum and local maximum, but instead of examining the first derivative, you're going to be examining the second derivative. The concavity can only switch from either negative to positive or positive to negative. That can only happen at places where f of x is equal to 0, or double prime of x is 0, or f double prime is undefined. So, like looking for local extrema, we're going to, instead of looking at the first derivative, we're going to find places where the second derivative is equal to 0, or the second derivative is undefined. And once we have that list of candidates, we're going to check if the concavity changes. And this is, again, similar to like a first derivative test, but you're checking the second derivative. So let's take a look at the problem that we have identified here. Let's find all the points of inflection for the graph of 2e to the negative 2x squared. So our first task here is, well, let's figure out what are the derivatives. What are y prime and y double prime? First of all, we're going to identify that we're taking the derivative of 2e to the negative x squared. And if you remember the derivative of an exponential function, that's the same exponential function multiplied by the derivative of the power. So we get the derivative equal to 2e to the negative x squared multiplied by the derivative of negative x squared. Now the derivative of x squared is just negative 2x, giving us a derivative of negative 4x e to the negative x squared. Remember, the derivative of negative 2x of negative x squared is negative 2x, and the negative 2x times 2 is negative 4x. Okay, what is the derivative of negative 4x e to the negative x squared? Well, for that one, you're going to need to use a product rule. You have two two factors, negative 4x and e to the negative x squared. So here is the derivative of the first derivative. We've broken it up into two factors. Negative 4x is the first factor, and e to the negative x squared is the second factor. And now we just use a product rule. Okay, there's my product rule, the derivative of negative 4x multiplied by e to the negative x squared, plus the derivative of e to the negative x multiplied by negative 4x. After all of those derivatives, we get negative 4 e to the negative x squared. And then the derivative of e to the negative x squared is the derivative of the exponent, negative 2x, multiplied by e to the negative x squared minus 4x. We're going to do a little bit of algebra to simplify this. That gives me negative 4 e to the negative x squared plus 8x squared e to the negative x squared. And if you factor out a factor of 4e to the negative x squared, you get what I have here, which is, well, what is that? That's 4e to the negative x squared multiplied by 2x squared minus 1. So that's, well, welcome to derivatives. That's quite a review. And like we stated before, in order to find those points of inflection, we're going to take our second derivative and we're going to find out when is it equal to 0, when is the second derivative undefined. And the reason I like to have things factored out the way I have them is that it's easier to do this part where we find out where things are undefined and where things are equal to 0. Because looking at this second derivative here, well, e to the negative x squared, we have two factors, and if either of those factors are equal to 0, we'll get a 0, and of course, if either of those factors are undefined, we'll get undefined. The undefined part is more difficult for a lot of students, but e to the negative x squared, that's never undefined. And then 2x squared minus 1, that second factor, well, that's never undefined either. So really it's sufficient to say when are either of these factors equal to 0. Well, this first factor here, 4e to the negative x squared, well, that factor is actually never equal to 0. That's asymptotic with the x-axis. You can take a look at the graph of it if you like, but that is never going to equal to 0. But the second factor is going to equal to 0. And so we'll write that out. So if you solve that out, 2x squared minus 1 equals 0, you're going to get negative 1 over root 2 and positive 1 over root 2, or if you prefer, negative root 2 over 2 or positive root 2 over 2. Now, what about when is y double prime undefined? Well, that's never going to happen. This is never undefined. This second factor, that's never equal to 0. And this first factor here, well, that's never equal to 0 either. So our only two candidates for a point of inflection are negative 1 over root 2 and positive 1 over root 2. And let's see where that takes us. Okay, so next we're going to create a number line with those candidates and the sign of y double prime below. This is a lot like your first derivative test. So let's see what we come up with. And that looks pretty good. Here's our candidates for our points of inflection. Notice that above the axis, we're labeling that x. Below the axis, we're labeling that y double prime, telling us where we're supposed to substitute. Over here on the left side of negative 1 over root 2, we've got positive second derivative. Over here to the right of root 2 over 2, we have positive second derivative. And over here, between negative root 2 over 2 and positive root 2 over 2, we have a negative second derivative. So that is sufficient to just figure out where we have points of inflection. Now, you're going to have to write this up explaining in a summary about the second derivative and how that works. So the graph have y has points of inflection at, well, negative root 2 over 2 and positive 1.2130 and positive root 2 over 2 and 1.2130. Remember, those are y coordinates, so you're substituting them into the original function to get those y coordinates. Because the second derivative changes signs at these points. Okay, so this is how we're going to write a summary that references the second derivative, and you have to reference that second derivative and changing signs in order to really maximize your credit. Okay. Finally, based on the shape of the curve, it's possible to actually analyze local extrema based on that second derivative. So if we visualize a second derivative being negative, here's a negative second derivative, concave down shaped like a frown, you'll notice that if there is a critical number, let's say right over here at the top, then that would be indicative of a relative maximum. Other way around, if we have a concave up function and we have ourselves a point, with the words escaping me right now, if we have a concave up function and we have a critical point, that means that we're going to have a relative minimum. And that's all the second derivative test says. It says that if we have concave down at a critical point, that means that we're looking at a relative minimum. And if we have concave up at a critical point, that means we're looking at a relative maximum. I think I had that backwards, so let me rewind it. If we have concave up at a critical point, that means we have a relative minimum. And if we have concave down at a critical point, that means we have a relative maximum. So I think this look backwards here for me, because this is concave down, and this should be a relative maximum. So let's go ahead and change that for you. Okay, that looks a lot better. Typo, it happens. So the second derivative only is going to work if f prime is equal to 0 and not undefined. Because if f prime is undefined, well, that means that we're going to be looking at a cusp, and the second derivative is not going to exist there either. Of course, if the second derivative, if you have a critical point and the second derivative is undefined, then the second derivative test isn't going to tell you anything either. But the second derivative test is actually a real favorite with people who write the AP test. So be aware of that. You will have to use the second derivative test. There are ways to create a problem which you have no choice but to use the second derivative test. So get used to it. Try and figure out what it is. And usually, just with my finger creating concave up, I should be able to figure out that that's a relative minimum. And then with my finger, if I go concave down, I should be able to reason that I have a relative maximum. So it's a pretty easy one to remember, in my opinion. So, you don't really have an excuse. Let's take a look at this problem. Let's use the second derivative test to locate all local extrema of y equals x cubed minus 6x plus 5. Notice that it's not really a problem to use the first derivative test on this particular function, but for scholastic purposes, we're going to practice our second derivative test. So the first step, let's find the first derivative and locate all critical values. Let's do that first. So my first derivative is 3x squared minus 6. First derivative, 3x minus 6. Now, if we factor out a 3, we get 3 times the quantity x squared minus 2. Now we'll find the local extrema by setting our first derivative equal to 0. And we notice that we get, we come down to eventually x squared minus 2 equals 0, which means that our critical values are, negative root 2 and positive root 2, because that's where y prime is equal to 0. Y prime is also undefined never, so it's important for us to reinforce that you are also looking for places where the first derivative is undefined. Okay, so step 2, find the second derivative and evaluate y double prime for all x where y prime is equal to 0. Really, that should say for all critical values. So let's scroll this down a little bit and see what we get. So we get a y double prime of 6x. And so when I substitute my critical values, let's see, 6 times negative square root of 2, well, that's negative 6 square root 2. Clearly, that's negative. And then when I substitute positive square root of 2 over here, I get myself a positive 6 root 2, which of course is positive. So that should be enough to tell me whether or not I have relative minimum or relative maximum at those two critical points. Scrolling down from here, we can summarize and say that the graph of, and this is nicely filled in for you too, the graph of x cubed minus 6x plus 5 has a relative minimum at, and let's think, we have a relative minimum if we're concave up, and we're concave up at positive square root of 2. Similar in analysis, the graph of x cubed minus 6x plus 5 has a relative maximum. That's if we're concave down. So where are we concave down? We're concave down at negative square root of 2. So we have a relative maximum at x equals negative square root of 2, because y prime is 0 and y double prime is less than 0. Okay, so that's our summary. Always with your summary, you want to reference the exact function, whether by name or by equation, and you want to link to that relative minimum and maximum to the first derivative and the second derivative. Okay. Reference the function, link the critical number to the first derivative, link the critical number to the second derivative, and then you're going to have a good summary. The following table summarizes all that information visually. You can go ahead and take a look at that. And that brings us to our important ideas. So what were the important ideas for this section? Well, there were a lot of important ideas. First of all, concavity. That's the rate at which the slope is increasing or decreasing. Maybe it's not a rate, but it's whether or not the slope is increasing or decreasing. Visually, we can say the concavity, concave up is shaped like a cup, concave down is shaped like a frown. Points of inflection are where the concavity changes either from positive to negative or negative to positive, and those will only occur, points of inflection will only occur when f double prime is equal to 0 or f double prime is undefined. And finally, we have our second derivative test, which can be broken down into 3 parts. Number 1, locate the critical values. Number 2, substitute those critical values into the second derivative. And number 3, if you have a critical value and concave up, you have a relative minimum. Critical value and concave down, you have a relative maximum. So those are our important ideas. The check your understanding is again from White Zombie. And we're taking that same function, I believe, from 5.3 day 1. And now we're going to be looking at relative minimums and relative maximums. Start off by writing our function out. And I see I forgot a parenthesis at the end here. Hopefully that's not going to throw us off too much. Let's find our first derivative. Here's our first derivative. Since 0.0042 is a constant, we can just take the derivative inside the parenthesis, and that will work just fine. So we have our first derivative is equal to 3x squared minus 170x plus 1047. And after that, we're going to find our second derivative. So our second derivative is, again, just inside the parenthesis, 0.0042, 6x minus 170. Next, we can see that h double prime is equal to 0 when 6x minus 70 is equal to 0, and 6x minus 70 is equal to 0 at about 28.33333. Remember, I'm going to keep 5 decimal places for accuracy, even though the answer needs to be, or the exact phrase is the answer needs to be correct to 3 decimal places. But in order to do that, you're going to have to keep all other calculations with as many decimals as you're comfortable with. So we are using 28.3333. Next, let's put together a number line using the second derivative. So our second derivative, to the left of 28.333, we've got a negative second derivative. To the right of 28.333, we have a positive second derivative. So since the second derivative changes, concavity also changes. And if concavity changes, that means we have a point of inflection. So to summarize things, we have h of t is concave down from negative infinity to 28.333. H is concave up from 28.333 to positive infinity. And we have a point of inflection at t equals 28.333 because the second derivative changes signs. So that's it, everyone, with our second derivative and our 5.3 day 2. Hopefully this was a good refresher course for you, or maybe if you're learning this for the first time, maybe this really got you started on all of these concepts. So we'll see you next time with more calculus here on the Fourier Math class. Have a good day, everyone.